Hi, in this video I'm looking at finding the derivative dy dx for this equation here, x plus xy plus y cubed equals 16. Now this is a relation because x and y are so tightly integrated that we wouldn't be able to get this in terms of just y equals stuff. So we need to use a process called implicit differentiation. And the first step of implicit differentiation is we're going to take the derivative d dx of both sides of this equation. So we're going to have d dx of x plus xy plus y cubed. And we're going to have d dx of 16. And so now we need to actually have a look at playing around with derivatives of both of these sides. So to start off with the left-hand side, I'm going to multiply this d dx onto each of the three terms. I'm going to expand this set of brackets here. So I'm going to have d dx of x plus d dx of xy plus d dx of y cubed. And that's going to equal to, well, d dx of a number, 16 in this case, of a constant, is just 0. So this bit's just going to be 0. So now I'm going to take a look at each of these small derivatives in turn. The derivative of x with respect to x is simple. It's just going to equal 1. So it's going to be nice and easy. But the others are a little bit harder. I've got d dx of x times y. There's a y in there. And I've got d dx of y cubed. There's not even an x in that one. So let's have a look at each of these in turn. So I'm going to move over to the side here. And we're going to first have a look at d dx of x times y. And this one is actually a product rule, because I've got the product of x times y. And the product rule states that if we have d dx of the product of two functions u and v, then that derivative is u times the derivative of v plus derivative of u times v. So I've got u times v becomes u times the derivative of v plus derivative of u times v. So if we apply that to our problem over here, I've got u, which is just x, so I'm going to have x times by the derivative of v. So the derivative of v, which in this terms is y. And I'm going to add on to that the derivative of x. I'm going to have d dx of x times by v, which in this case is y. So I'm going to have times by y. So if we tidy this up a little bit, this is going to give us x times dy dx plus, well, derivative of x with respect to x is just 1, so this bit's just going to be 1. So I've got 1 times y, so I'm just going to be left with y. So d dx of xy is x dy dx plus y. So let's take a look at the next part of our derivative, which is d dx of y cubed. So we're going to have d dx of y cubed. Now this one is more of a chain rule style question, okay? And we're going to write the chain rule slightly differently. We've got d dx of some function in terms of x is going to be d dy of some function in terms of y times by dy dx. So it's just a generic d dx of some function in terms of x is d dy f of y times dy dx. So technically the dy's cancel out and I've got d dx of f of y, which is what we've got here. d dx of f of y. When I go to doing my derivative here, I'm going to have d dy of my function of y, which is this y cubed, multiplied by dy dx. So I'm just going to have dy dx in there. So if I look at this, d dy of y cubed, well, the derivative of y cubed with respect to y is going to be 3y squared, because we multiply the power down, subtract 1 off the power, and then it's going to be multiplied by dy dx, because I've just got dy dx there. So our d dx of y cubed is going to be 3y squared plus dy dx. So now I can go and put these into my derivative. So I've got d dx of x, which we've already said is 1, and then I've got plus d dx of xy, which we've worked out to be x dy dx plus y. And then I've got to add on d dx of y cubed, which we've just worked out to be 3y squared multiplied by dy dx. And that all equals 0. So now I've got this equation to play with. And so I've got 1 plus, and I've got this y here, which is also added on. So I'm going to have 1 plus y plus, now these two terms here both have a dy dx. So I'm going to have dy dx come out the front, outside of, and I'm going to be left with x plus and 3y squared. And that's going to equal 0. And so now I'm almost there. I've just got to isolate this dy dx because I want dy dx. And I'm just going to algebraically rearrange it so it's on its own. So I'm going to subtract the 1 plus y off of both sides. So I'm going to subtract that so it ends up over there. So I'm going to minus 1 minus y from both sides. So that way we have dy dx outside of x plus 3y squared equaling negative 1 minus y. And then I've just got to divide both sides by x plus 3y squared. So I'm going to divide this side also by x plus 3y squared. So that's going to leave me dy dx on its own. And I'm going to have the negative, I'm going to bring that negative out the front, of y plus 1 over x plus 3y squared. And that's our answer. We are done there. So it takes a little bit of time, and you've got to pull a few different differentiation techniques, but you derive both sides of your equation, break it up into the smaller derivatives, work them out using whatever technique is necessary, product rule, quotient rule, chain rule, and then sort out the algebra to isolate your derivative dy dx, and you're done. And that's the process of implicit differentiation.